The coefficient of determination. The correlation coefficient R can be squared to create what is known as the coefficient of determination, or the R squared value. There are several properties of R squared. Number one, the value of R squared, when you don't make it a percentage, but you keep it as the decimal number, is going to be between 0 and 1. Number two, the value of R squared describes the fraction, or you can multiply by 100 to make it a percentage, of the variability in your Y, or your response variable, that is explained in a straight line model, the linear model that you fit, when using the predictor X variable. Now what is left over out of the total, the one whole, is the 1 minus R squared, is that part or that fraction of variability in your response variable that is not explained in your straight line model when you're using the predictor X variable. You're always going to sort of interpret points 2 and 3 when you're describing or interpreting the strength of a linear relationship between your X and Y variables. Recall the correlation coefficient was R equal to 0.6926 for the weights versus tail lengths of wolves data. So if we take R and square it, we get about 0.4797 when we round off to 4 digits after the decimal point. So keeping it as this decimal number, we could write an interpretation that says 0.4797 is the fraction of variability in weights of wolves, which can be explained in a straight line or linear model with length of tail as the predictor variable. This leaves 1 minus 0.4797, or 0.5203, of the variability in weights of wolves due to random error. Now, error in this case doesn't mean a mistake, but rather it's the part left over. It's the differences or the variability that cannot be accounted for or explained in the current model. Now, if we go back and write the coefficient of determination as a percentage, we still take the R value and square it, but now we're going to multiply that 0.4797 by 100 and make that 47.97%. The interpretations will look the same, just with percentages instead of decimals now. So we would say 47.97% of the variability in weights of wolves can be explained in a linear model with length of tail as the predictor. And this leaves 52.03% of that variability in weights of wolves due to random error. You may work with the coefficient of determination in either way, really. You can do it as a fraction or a decimal, or you can do it as a percent. Just be careful not to write the decimal and then put a percent sign on the end, because to say 0.4797% of variability is explained in this particular model really is not true.